give a brief introduction about Dr. Ganesan.
Uh, Good evening to one and all. It gives me immense pleasure to introduce the chief guest of the day for the webinar Trends in Gas Turbine Engine Technologies. Dr. Ganesan is Scientist G and the Group Director of Afterburner and Exhaust Systems, ABES, Group of GTRE, and he is responsible for the design and development of afterburner and exhaust system for various gas turbine engines of GTRE. So as our HOD Dr. Vijayaraja sir said, he obtained his BTech in Aeronautical Engineering from MIT Anna University. My I am also an alumnus of the same institute in the year 1995, and he's in first class with distinction. Where he further obtained his MTech in Aerospace Engineering from IIT Madras in 1997. He earned his doctorate also from IIT Madras in the year 2006. From 1997, he has been associated with GTRE, so he is having a vast experience of around 23 years in GTRE. In GTRE, he is responsible for the design and development of afterburner, CD nozzle, and bypass duct systems of Kaveri engine and its spin-offs through engine and CFD analysis. He is the recipient of the Young Scientist Award from the DRDO in 2006 for his outstanding contribution towards the design and development of gas turbine afterburner systems. He has over 40 publications, both in international and national journal as well as conferences. Sir, it's a pleasure for us to be able to hear to you, hear you, and I hope all of them will have a very good webinar listening to you. Thank you. Oh.
Oh. Can I go ahead?
Yes,
Yes,
yes.
sir.
Yeah. Thank you, Professor Vijayaraja. I think inviting us. Basically, I like to go on offline than the online because of our. But the current situation, we like to move this forward. And also Azad for the introduction. And also I am like to thank all your other faculty members joining for this, as well as the students. So I would like to share what are our experiences. Even then, the presentation talks about the modern trends about the gas turbine engines. Little bit on the way, I'll try what GTRE trying to do on this also, so that we can have the little bit comparison about the overall. So that's all overall. So can I go ahead?
Yes.
Yeah.
Yes, sir. Sure. Please go ahead.
You are able to see my slides.
Yes, sir. Yes, sir.
Yeah. Okay. Thank you.
Yes, sir.
So
Yes, sir.
okay. So basically, in this presentation, maybe another half an hour to 45 minutes, yeah, maximum you can go to 1 hour. Before that, I'll talk about what, as a GTRE, gas turbine research establishment, what we are doing that. Then I'll go about what is a gas turbine engines, what all the innovation in this technology, where to move on the forward about the next generation engines. So GTRE comes around under umbrella of DRDO. We have nearly 50 to 55 different laboratories working from aeronautical to the even rubber technology, whatever the technology you talk about, electronics, all this. So as a GTRE, we basically work on the gas turbine engines. I think you are from the aerospace people. I came to know you from the BTech second year to BTech from second year to final year students. So basically, we'll develop the gas turbine engine to propel the aircrafts. Under that, our main area to develop the not only gas turbine but also technology required to design and develop the engines. Basically, we work from the small gas turbine engines to big engines. You talk about small gas turbine engines, we talk about 5 kilonewton, 4 to 5 kilonewton to the 50 kilonewton to the maximum range of 110 kilonewton. That kind of different class of engines will work on to that. So before moving on to that, I maybe give the slide movie about our GTRE that will summarize the overall what GTRE doing that before I'm going into the what are the technologies. Audio is okay?
Yes, okay, okay.
Okay.
GTRE, Gas Turbine Research Establishment, Bengaluru is one of the pioneering research and development laboratories of DRDO under the Ministry of Defence, Government of India. Gas Turbine Research Centre, GTRC, was established in 1959 at Kanpur with a mandate to design and develop indigenous gas turbine engines and allied technologies. GTRC was later moved to Bengaluru in the year 1961 as Gas Turbine Research Establishment. With its rich history of pioneering work in the field of gas turbines, GTRE's vision is to be a center of excellence for aero gas turbine engine design and development of related technologies. GTRE's mission is to design, develop and integrate advanced technologies, state-of-the-art aero gas turbine engines and their derivatives for defense forces. GTRE is an ISO 9001-2008 certified establishment and is committed to deliver reliable products through continuous improvement with the effectiveness of quality management systems.
The Gas Turbine Research Establishment is one of our premier laboratories under Aero Cluster with the mandate to design and develop gas turbine engines for military and industrial applications, besides carrying out advanced research work in the area of gas turbine subsystems. GTRE is also responsible for establishing the request, testing and prototype manufacturing facilities for components and full-scale engine. GTRE has designed and developed Kaveri engine, a 80 kilonewton thrust class engine, and that had been test flown in flying testbed in Russia. It is undergoing endurance tests in GTRE test beds. A spin-off to this program, GTRE has developed a marine version and demonstrated 12 megawatt power supply with the specially designed power turbine. A new dry variant of Kaveri is under design and development for future applications. Most recently, GTRE has designed and developed a small turbofan engine, Manik, and demonstrated full thrust at 100% RPM.
GTRE has established in-house facilities for aero-thermodynamic performance evaluation of critical modules. Extensive structural test facilities for evaluation of various components and subsystems have also been set up at GTRE. GTRE also has extensive manufacturing and prototyping facilities. These facilities have enabled GTRE to develop indigenous gas turbine engines as well as allied technologies. Today, GTRE works with some of the most sophisticated technologies in the gas turbine industry. Realization of these technologies have helped GTRE to develop state-of-the-art aero gas turbine engines and its other spin-offs. Over the years, GTRE has acquired expertise in carrying out computational fluid dynamic simulation. These simulations enable GTRE to numerically investigate the strength, life and performance of critical components under various design and off-design conditions. With its top quality personnel, GTRE has also registered several national and international patents and copyrights against its name. With its rich experience and credentials, today GTRE is proud to be the flag bearer of India's gas turbine design and development program.
Yeah, that is very short, maybe more than 5 minutes slide about whole what GTRE we are capable or what we are doing that. Right now, I'll go on to the gas turbine engine, whatever the title of the today talk. So you talk about any engines, yeah, gas turbine engine much complex than any of the human being into that. And you have seen the whole GTRE, whatever our capabilities, what all the technology involved from you talk about from normal aero background into a mechanical, electrical, whatever the field you are talk about, all are there or is required to develop any gas turbine engines. So now I will talk about the gas turbine engine technologies, and if you not able to follow set up the technology, forget about that, you just know the keywords, later on you can find out what was that. Otherwise it's overall about talks about what is the technology right now, what is the technologies evolved, what is the present status. So if you talk about any gas turbine engines, so this is where you can see the any aircraft, you can see that engines buried into the aircraft. So that engine you call the heart of the engine, you call a gas turbine engines. So basically you talk about any gas turbine engines, just to take my pointer. So sorry, any gas turbine engine you talk about that, mainly it have the three main component. The one you talk about the compression, whatever the incoming flow comes from the engine, it has to compress it to the required level. So it is done by the compressor. That is the first part of the component. Then once you have done compressed sufficiently, you add the fuel, burn it. That is called as a combustion chamber. Third one, whatever the energy developed, you just to try to pump onto a turbine engine, it will try to extract the energy to rotate the compressors. This was a simple terms of a gas turbine engine. The remaining part, this is the core, we call it the core engines. Remaining part, you can add more number of stages, means more number of compressors, more number of turbine, you can add downstream as well as upstream. This is basically a simple gas turbine engine in base principle. Yeah, this is way putting that. That is very simple way. But if you talk about any engines in the gas turbine engine, you talk about people talk about low pressure, high pressure. So I told you talk about the main compressors, combustion chamber and turbine. But you can keep on add more number of components. If you add in between one compressor, it's called as a fan. And sometimes people use the single two stage. If you talk about three stage, people use fan, high pressure. In between, they call about low pressure. So number of stages you can increase based on the what is the requirement, how much energy you require, or how much pressure is you require. Based on that, you can add, keep on adding to that in the front side. Similar way, you can add the end also based on number of compressor you have. Similarly, you can add number of turbine also based on requirement. So the whole thing, if you add it, basically it comes the two type of applications. One talks about the civil aircraft I think most of the people are familiar with. The second one is the application for the military aircraft, where we are doing for that. The requirement for the you know that for the civil as well as the military aircraft is totally different. So my experience basically on the military aircraft sites, but I will touch upon wherever required for the civil aircraft side. I will just to give the highlight onto that. The requirement, if you talk about that, people talk about low SFC, specific fuel consumption, because we are paying the money for our air ticket. So we should able to use very effectively our fuel, so that your fuel consumption per kilometer per journey should be as low as possible. So we talk in terms of physical fuel consumption. So you talk about a physical consumption, but basically talks about minimum fuel to be used, that one, so that your air ticket amount will be very less. Second, you talk about the comfort. So we are sitting in the, we want our journey as happy as possible, so we want comfort. And also this too is for the human. The second one, we are living in the environment where the emission is going to major role wherever the near the airport. So low emission also very very important. So these three parameters going to decide what kind of engine you should develop. According to that, you have to do that. The military aircraft side, what we are working into, that we not bother about the any of the above. So we look for the super maneuverability. You know, most of the people are familiar with what is maneuverability. So we want to go at any speed, attack anybody, come back to your own places. The second one, talk about super cruise, means that you should be able to hide or somehow get your maximum engine performances without showing into the your where is the engine is there, how much the temperature showing, the enemy should not detect. So to not to detect, what kind of technologies use, so that still you can able to do the super maneuverability. The third part, you talk about stealth. So it should not shown that we are flying into enemy directory, all this, what kind of stealth technology. The other most important, we should have the high thrust to minimum weight of the engine. And we should go to, because you talk about all civil aircraft, you talk about all the subsonic speed, because you know the most of people Mach number, it should be less than 1, around 0.7 to 0.8. But in terms of military, we never bother about the subsonic. We want to go the supersonic more than Mach number 1 and do that needful. So that's for the aircraft. So if we convert that technology into a engine requirement, because end of the day, as a engine designer or the aircraft designer, finally today I'm talking about the gas turbine engine. So how do a gas turbine engine based on the requirement converted into that? So basically both engines talk about, I think you can see based on the slide itself, you can see that how both engine looks different from that. So you maybe seen all the aircraft civil side, the huge fan, maybe 2 to 3 meter sides. But if you talk about military engines, it will be a less than the meter your inlet diameter, because we are talking about the frontal area. That should be a minimum as much as possible for the stealth and other point of view. So here we talk about the three important parameters. One is the bypass ratio. So how much air you can bypass, how much air it can goes through the engines. So that will decide the how much the bypass ratio, because to get the low speed, you require the high bypass ratio. To end of the day, your mass flow rate into velocity will dictate the overall thrust. So if you have the bypass, you can, your speed will be low, still you can get your required thrust. Then, because you always get the energy when you can able to compress your incoming air from the normal atmosphere to the around 30 to 40. So you compress it. Second one, what kind of turbine entry temperature? This is a bypass ratio, bypass pressure ratio, this is overall pressure ratio, and this is a turbine entry temperatures. So what kind of temperature it can go to the turbine, so that you can able to do them. So this turbine entry temperature will decide what kind of combustor you should have. So based on that, you should arrive it. But in terms of military engines, you talk about, like I said, no, we looks high thrust, all this. So if you talk about turbine and temperature, we are not worried about what the, because here the number of operation will be more, but in the military side, our number of operation will less. So you can go for higher temperatures. Like I said, your bypass ratio, here you talk about 6, even 10, but it will be always under less than 1. And the pressure ratio will be, this will be 30, but it can always lesser than that. So in addition to your gas turbine engine, you will have one more engine for the military sites. Is talk about afterburner system, where you can have the burn the fuel air after the turbine and get it. I think this movie is not working a little bit. So that is called is a gas turbine engine with the afterburner. So this you can see that on your engines, you have the combustor, so flow through that. In addition to that, you can have the afterburner. This is basically will be used in the military engines. So my area of concern is only this area. I put my effort last 23, 24 years in this area. This is your turbine one side, then comes to the afterburner. The first component you have the this one, then we have the flame holder holding the flame. Then this the afterburner will be utilized to get the whenever the extra thrust. But this is not a continuous operation. In the whole flight envelope, if you 1 hour flight, we'll have the maximum 5 to 6 minutes time, so that your fuel, I talk about fuel consumption, because the fuel consumed here will be a much maybe 3 to 4 times higher than the main engines. So whenever required, when you want to chase your enemy, you suddenly put your afterburner on, go and chase and come back. But this you can see that it won't be there in the your civil side. Civil side you will have the, like I talk about this core engine, that only low, but the size you can compare the size, it will go bigger and bigger, so that more mass flow can come in, you can do the jet thrust. So this is a typically what are the parameters each side. If you look at it, if you talk about compressor, mainly you look at the compressor, turbine, afterburner, how typically a flow parameter. Based on this is because this all as a students you require to know that when you pass through the each this one, what is the pressure is changing, how the temperature is changing, how to predict that one, what kind of material required, what kind of manufacturing technology you have to use. The whole thing can be understood from this simple graph. So now if you talk about any aircraft engine, like I told now, if you some of the terminology, if you are not able to follow or it is different, forget about it, at least you know so many technologies around that. These are the typical names. Later on you can go to the Google and search for that, what is that on. So once I talk about now basic fuel consumption, that is very much important. Thrust to weight ratio, then you talk about the geometry, where is your weight, what is the CG with respect to your aircraft should come into that. Then to able to operate, what kind of margin you have in terms of the vehicle stall. Stall is nothing but separating from the blade. In simple airfoil, you keep on increase your angle of attack. At a certain angle of attack, your airfoil will separate it. That in terms of blade, we talk about stall. Then you required, because you have some pilot will be there, so you have to give him some kind of breathing. So you have to give some kind of customer bleed to him, or further other accessories to operate it, so that that will come from the engine. Then remaining other accessories. Then second you talk about the military side. This is not a civil side. You require to able to operate or rotate your thrust particular directions. And the other one talk about the life. Then once you have developed the engine, you should see the how to maintain the engine and how logically you have to support throughout this career, all this. And also you should know the complete flight envelope. What is your, is this uninstalled thrust means without aircraft, without intake, all this you take. When you install thrust, when you fit it in the aircraft, what kind of thrust it to go. As an engine developer, we won't talk about the how much it is. Finally we talk about as a uninstalled thrust, how much will come from the engines. Then you should be able to demonstrate the performance or the complete is envelope. Where are you are looking for that? The least part, even then we are not worried. Stealth also important, but it is much more important for the civil aircraft sites. So what are the technologies? This I told now, as a student you can pick up any one of these technologies. You require aero thermal, because you have to go through all the, whether in terms of computational fluid dynamics or the structural analysis or the material and manufacturing, you have to go through all this. So you require a strong background of aerothermodynamics material, because you know that, like I said in my previous slides, I put the temperature and pressure plot over the engines. So each component, you know what is his temperature and pressure, correspondingly you choose the material, and each one you should have what kind of technology you have. Then you do the structural analysis as a system, because only I talk about the gas turbine engines. So some of the, like a gearbox or some kind of secondary air system, rotor suppose, which as a aeronautical student we may not study, but as a mechanical engineer is supposed to record a rotor dynamics, how is going to rotate all this. Then basically we should be able to operate from the control room, giving only one command that the aircraft engine is able to operate it. And the other one is how the component over the time. We define in terms of life of 100 hours or 10,000 hours. Like in military aircraft, we'll talk in terms of 1,000 hours. But in talks about civil, they talk about 10,000, 20,000 hours without overhauling the the engine you should be able to support. And during the process, something happen, how to monitor it. That is one of the critical technologies. Somebody have the instrumentation and other background. It's very much useful to monitor continuously and then do the action. And during the design development time, you should be able to integrate as you do as a component and testing. Finally, you be able to get it from certification also. Yes, this engine can be put into the service. So typically, this is a typically you talk about any gas turbine engines. This is I'm talking about the military engine. This is one of the latest aircraft engines. You can see that. So basically, they talk about two spool. So two spool, nothing but two kind of shaft will be available to drive. So means that you have two compressors. One is called the low pressure compressor. Other one is a high pressure compressor. The civil side they'll have the three. I think more than three is right now is not that. It's sufficient to that. So what kind of fan technologies? Because nowadays people talk about wide guard, normal guard, single crystal. I think that's all the manufacturing technologies are there. Then if you talk about like I told now, LPC means low pressure compressor. That's a one stage. We call this one stage. Then high pressure compressor is the second stage. So the low pressure, what kind of pressure means? What kind of technology you have to achieve this? How much pressure required? And what kind of mass flow required? This is a high pressure compressors. Then as a I told turbine, this is called a turbine entry temperature. How much technology? This basically you want this flow going to hit the turbine blade. So what kind of material technology you have? Based on that you have limit. As far as the technologies concern, you know that if you try to burn any fuel in the combustion chamber, you can go maximum 2200 K. If you have the technologies, still you can go out, but most of the material availability will restrict it lesser than this. This also with cooling. So here only next point, what kind of cooling you have and whether you have the coating also available onto that. Then finally the nozzle, what kind of material available to that. So this always talks about overall. The same thing is translated in terms of number. What is your overall diameter? What is overall pressure ratio? What kind of bypass ratio? What is the length? Finally, end of the thrust. So finally, we talk about that. This is you talk about thrust of the engine. This already given here. Thrust to weight ratio. We talk about around 5 to 6. That is dry means without turning afterburner on. With the afterburner on, you will get the additional thrust around 30 to 40% more. So you will get. So right now, all the military engines you talk about thrust to weight ratio in this class. But if you talk about thrust to weight of civil aircraft, that all will be lesser than that. And finally, I said you want to deflect your thrust. So based on that, what the direction you can lift it. So this is basically a gas turbine engine, and then what are these numbers. Now I'll go to my main topic about what are the technologies. If you are not, that's what here. If you are not able to follow, leave it. So first is I told about the compressors. So compressors, you have the air, you want to compress it high as possible. So what kind of technologies uses? So there are two technologies involved. If you can see any textbook or any literature, two kind of technology. Only they call multi-spool, means the multi-stage compressor, you can call it. So like I said, my earlier one, you can have the single stage or the two stage or three stage. So based on how much pressure ratio you require, that many number of compressor you use it. So basically the Pratt & Whitney, if you talk about, they will use this kind of technology to use it. The second technology is that even with a single spool, you can able to get it. That is a different technology they will use, because the blades, you can have the variable in such a way that you can use it. So this two kind of technology you can use to get your compression ratios. So if you talk about variable slot, if you don't know, sort of leave it. But basically, you have the different type of compressor. Only a single spool or the multi-spool, single stage compressor or two stage compressor, three stage. Based on that, you can achieve that one. So this you talk about the blade. That's why I told you, if you see in any civil aircraft, it looks like that. Like I told my earlier blade, the wide guard. The earlier blade you talk about very straightforward. Now you can go with modern technology and manufacturing technology. You can go highly composite material all this. So if you talk about in the initial stage, each stage means you have to compress it. You require one continuous rotating part, one stationary part. The continuous part is called as a rotor. The stationary part is called static. That's called the single stage. In a single compressor, you can have multiple stages to achieve the required pressure. But in a given stage, if you talk about in your early gas turbine technologies, we talk about 1.1 to 1.2. But now, yes, you have a lot of modern technology, lot of prediction technologies. You can earlier the difficulty is that if you know that if you go more than Mach number of 0.8, you'll get the shock. If there is shock means there is a loss. That is, you don't have prediction mechanism how to suppress that also. But now we have the lot of technology improved into that. People now even the blades are running around 1.2 to 1.3 Mach number without any trouble. With that, we can achieve pressure ratio. Means that if you talk about 7 stage required in 1950s, now within 1 or 2 stage you can achieve kind of pressure ratio you require for that. So that's I talk about fan means the first stage. Second, you talk about the overall pressure ratio. As put like I said in my first slide, maybe single stage, 2 stage, or 3 stage. You add as number of end of the day. The requirement is if you talk about we talk about 5 to 6. You know, most of people Vittel engine is a first aircraft engines. It is you can talk about pressure ratio of around 5. Now we can talk about. So this all the top side is talk about civil engines. Bottom we talk about the military engine. You can see that the pressure G is the latest engine. I can all the Boeing 747, 787 driving. You can see that it goes around pressure ratio around 50. With if you see that the number of stages not more than 5 and 6. So that comes from your modern technologies. So now I think everybody studied about gas turbine engines. I think most of the students familiar with. We will always talk about Otto cycle, diesel cycle. Also similar way gas turbine also. We talk about the efficiency. Why I told efficiency, we talk about the pressure ratio. Where we will, because whenever you, as your students, suddenly I talks about the pressure ratio, what for is required. So you should be able to relate it. So one way relate, you studied single function is called efficiency or the thermal efficiency. That related to your compression ratios. So as much as you are the higher the pressure ratio, you'll get very good compression efficiency. Sorry, thermal efficiency. So this is a typically you can see over the years your thermal efficiency basically is improved from that. If you talk about current engine, this you talk about at the time of your Wright brothers, we talk about 10% of thermal efficiency. Now we can go around civil side lightly higher side on 30%, 40%, and military inside because we have constraint, we cannot go more pressure ratios, so it will be around 30. So that must jump in technology over the years. That related that the second one I talk about the bypass ratio. So how much the bypass ratio you talks about that. This is basically comes to the second kind of efficiency. I maybe will come down a little bit late. So this is a military engines. This is a civil engines. The civil engine, how much bypass air you can able to divert. This is also similar to that. If you talk about the initial stage of pressure ratio 1, now we are talking about the new engines around the pressure, the bypass ratio around 10. So the similar to the compression ratio, bypass ratio you all. So this is comes from the two kind of efficiency. The thermal efficiency talks about the compression, this one. The other one talks about the component efficiency. You put together whole thing is called the propulsive efficiency. Somebody maybe studied what is the propulsive efficiency. So you have the engines. So you have the fuel input comes into that. That is a thermal output. That will output by input talks about thermal efficiency. But whenever the energy comes out of the nozzle, how you are going to propel your aircraft, that comes to your propulsive efficiency. So put together, if you talk about thermal efficiency and propulsive efficiency, that comes about the overall efficiency. Here we put the component efficiency and cycle efficiency. That will dictate about your thermal efficiency. And propulsive efficiency is the other one. You multiply both, you will get the overall efficiency of the a given system. So next other one I talk about the basic fuel consumption. So when I talk about thermal efficiency, it's directly related to the compression ratio. In between also I told that is called the propulsive efficiency. We talk about the propulsive efficiency. The overall efficiency is multiplication of your propulsive efficiency and thermal efficiency. So if you combination of that with some constant, you multiply all that, that will decide what is your specific fuel consumption. So higher this, you will get lesser. So end of the day, higher the propulsive and the thermal efficiency, you will get the royal fuel consumption. That's why we are looking for that. So that can be achieved. Other than these two parameters, it comes into the your combination of bypass ratio, overall pressure ratio, what kind of turbine entry temperatures. I think if you studied the gas turbine in any of the gas turbine course, this terminology very easy to understand this. So you can see that initially we talk about the thermal efficiency. You take only number, don't look at the seriously what is that. Basically, you talks about one as a one. Right now, if you talk about, we talk about 0.5 to 0.2. Basically, it talks about this military side. We talk about 22 grams per kilonewton of thrust. You talk about civil side, it will be on 50 kilogram. Sorry, in the civil side, it will be around 22 grams per kilonewton second. On the military side, it's around 50 to 60 grams per kilonewton of thrust per second. That much fuel will be consumed in the modern tent. The next technology, now we talk about the how the compression plays the role, what all is terminology, what all is efficiency, how you dictate. Now you have increased your pressure, what you are going to do next. So I have now high pressure compression. What I will do with that? I have just I added more number of compressors. What I will do? So I should get something out of that. Can you get it? Without adding its energy, nothing will happen. So I have to use the next component, talk about the combustor. So I have to, this high energy comes from the your compressor. I have to add the fuel, burn it, and then throw it in turbine. It go and hit your turbine. Turbine going to rotate. That in fact going to drive the your compressors. If you talk about over that, I won't go so much detail. Just to know the key terminologies in the whole gas turbine engine. Because I have worked in this area, so most of this is very complex, and most of the compressor or turbine, you can have some kind of methodology or some kind of understanding. You can able to model it or do some kind of analysis and do it. But this is very difficult. I always call it a black box. We don't know what is happening. You add the fuel. I know end of the day I'm getting temperatures. How is getting temperatures? What kind of chemistry I have to use, because we are not the chemistry background. Even I don't know what is chemistry on, but still we'll use fuel, we'll able to burn all this. So he basically talks about this will relate what kind of technology you are going to put in terms of emissions. So if you talk about initially, people talk about NOx, that is one kind of emissions, high NOx. And if you talk about, this is called air to fuel ratio, how much air available, how much fuel you can add. This is the region of stable operation you have to operate. The initial regions, people talk about, this is called leaner side, means you have the less fuel you operate, then you have the stability problem. But if you have the more fuel you add it, then you have the other high NOx problem will come to the. So somewhere you have to optimize such a, this is a psychometric. I know everybody knows that the right amount of fuel is required to given year for to make, then you do it. But we won't operate near to that. We'll somewhere operate away from that, so that we can able to use effectively the fuel. So the technology, if you talk about the first one, we have the single combustors. You burn more rich, means more fuel you add it. Down the line, you add more coolant through that, you mix it such a way that you can get. But nowadays, people have used different technology to control the, basically the NOx is the emission. This is basically will be used in the civil engines. Military engine will go with the single kind of combustor, because we are not worried about NOx or any emissions. Here we have the different technologies, low fuel, low lean blow, or the low burn technologies. They have radially, they have two-stage of compressor. Actually you can have the two-stage. So, and you have multiple, maybe you are seen the nowadays cars also have the single point injection to the multiple injection. Some of the points will operate certain operation, some of them will operate in some other operation. When you go high speed, all the points will operate. The similar kind of concept used in the aircraft industry also to get the combustions. The second part is the turbine. Turbine, as you know, it is same as your compressors. It's a blade consists of number of stages. If you have two stage, similarly two stage turbine is required. But now you are throwing your temperatures around 1800 to 2000. Whether your blade able to withstand all this. If you talk about any blade without cooling, you can go with the gas temperature around 800 degrees Celsius only. So if you go have a lot of cooling internal passage, still this is, I'm talking about turbine entry temperature. This gas temperature means turbine entry temperatures when flow entering through. You can go 1400. So you are not changing the material, same material, but you have done a lot of analysis, type of cooling, lot of heat transfer studies. You do it such a way that what kind of cool, where to put, how to put it. So whole technology involved, what kind of cooling patch is required. As a simple problem, as a student, you can take any blade, you can do a lot of analysis, find out its temperature profile, then drill the hole wherever you want it. In addition to this cooling technology, you can coat it thermal barrier coating over the small layer over that. You see that another 100 degrees Celsius it can be increases. So one is you have turbine blade, what kind of this available with that blade, you can different cooling technologies, you can able to increase the your turbine entry temperature. It's going to give you more thrust, as well as you can have the cooling technology, you can operate over the longer time. Second, we talk about the materials. I think if you studied anything, they started with the titanium alloy. Now we can talk about nickel-based alloys for the super alloy. We call this a super alloy. You can see the combustor initially all are metals. Now we talk about it's basically you can use it for the any metal with elevated temperature without any trouble you operate. That is called super alloy. These all alloy of nickel, or cobalt, or Haynes, some kind of this. You can see that even all the some of the parts like a fan, all this now people are going for the composites. So including from metallics to non-metal to the composites. So as long as you can go with the different composite, you know that what is the advantage with the composite over the metal, you can able to reduce your weight. So in terms of as a aeronautical engineer, you talk about you are going to improve your thrust to weight ratio. Your weight going to down, so your thrust with the same thrust, you will get the higher thrust to weight ratio. That's why we are looking for that. So that is over the technology. You can see that you can see the any gas turbine. This is typically you can see that on low temperature regions you can use titanium. You talk about the high temperature regions, you talk about super alloy. Similarly, these regions you talk about from combustor to upstream, all the titanium alloy composites you can use. The high kind of regions because the operating temperature very high, so you can choose highly elevated temperature material, basically is a super alloy. So this is overall in terms of turbine entry over the year, because I'm talking about the innovation over the years, so we'll be able to compare it. So single crystal means that's one of the manufacturing technology to produce a turbine without any grain boundaries. I think you can study any manufacturing technology, what are the different technology involved. I'm not going to talk or tell about what kind of technology required. It's basically one of the technologies. You can see from uncooled to the cooled and uncoated blade. And now at present we are in this region. Even CMC means ceramics matrix composite. People talk about ceramics matrix also to use. We are also working towards some combined component to use this. So over the time you can see that how gradually we improved to get the technologies. Second, we talk about the manufacturing technologies. We talk about conventional blade and this. Nowadays we talk about blisk. This blisk means you initially you have the rotor blade and then the shaft. Now you can integrate it. This is called the blisk. You integrate it as a single component. And the second one, you can try to reduce. So you can see that this component you can reduce it. You can able to reduce the weight from conventionally 100% to 30% reduction in that. Right now with the titanium, all this, you can able to reduce your weight to 70%. And the other technology we talk about the nozzles. Initially you talk about all the nozzles will be straight. Now we can maybe you can see in some movie also, you can move the thrust to 90 degrees down. That's basically any hover aircraft you can see that can be used. But this is the military side. You can see that with the nozzles you can able to thrust instead of rotating your airfoil or the wings. You can able to use your instead of control, instead of airfoil or wings, I'll tell instead of control surface, because you are not an engineer, so I can use the right word. Instead of your control surfaces, you can use your engine nozzle flaps to rotate your thrust, so that whatever the engine operation required, you can able to do that one. So the whole thing finally comes into that from the present olden technology to now. Finally, I'd say as a gas turbine engine, you look for the compressor, combustor, turbine, all this. As a overall is a system, you require thrust or thrust to weight ratio. So we talks about 0.6 kilonewton, your first flight in 1903 to now military engine, we talk about 160 kilonewton. You can see the jump over the years we achieved. If you talk about, this is for military, but see, this is a civil engine. Any of the your commercial aircraft, we talks about another 5 times more, around 500. This is I'm talking about single engine. You may be seen that some aircraft with this single 2 engines or 4 engines. So single engine from this is basically this much you will achieve from your bypass ratio. This will be bypass ratio around 10. This will be no bypass ratio less than that. If you increase the more bypass ratio, you can able to achieve as much thrust is required from the engines. So this is finally converting into a number in terms of putting a lot of technology I told from how to thrust to weight ratio. So initially less than 0.6 to 1903. Now the military engine I told now we are around 5 to 6. In fact, with the afterburner you can achieve 9 to 10. And all commercial, this is a civil side. It will be a 9 to 7 to 9. That is the range. So you can see the over here different engine. I think these are the engines used for the different aircraft. This is basically like a civil. This is on military side also. So whatever I have summarized, it talks about this one. Actually, this one slide only I have talked in the split, and I have talked about this. You're talking from 1940 to your first engine to the 2020, the new engines. We talk about the different compressor, different cooling technology, different manufacturing technologies, different kind of manufacturing technology. The technology evolved over the region without a straight turbojet engine to a turbofan engines, a single low turbofan engine to high bypass ratio engines to the modern technology. So this one slide, whatever I put, maybe 15-20 slides, summarize the over the technology reached from 1940 to 1920. So now how to move? I have another few more slides only, so I will restrict it to less than an hour. So few more slides to go on. So what we have to move on to the further if we want to develop the engines. Now we are in the 2020, we want to move another 10 years. What is the roadmap for to move forward? So now, like I said, now one technologies people are working that we talk about like a turbojet engine, turbofan engine, turbo prop engine, all this. Why not to work on the variable cycle engines so that when you operating at the requirement of the turbojet required for military engine, you should be able to operate it. When you want to have the turbofan where the SFC is very important, you can use it on the, still in the conceptual stage. So people are doing that. I think GE has developed some kind of 3 variable technologies used in the cycle calculation itself. And this too is the double board combustor technology, what kind of technology you can use it. And this it talks about your fan, what kind of manufacturing technologies. And this is for the engine technology. You talk about the material, we have to move towards the composites. As for the GTRE concern, we basically working on the metals, but we are trying to move on to that. And scientific and smart material technologies, we have to do that one. What kind of tool required? We have to end up the design, test your engine, and what kind of a simulation required. You don't need to put the engine in the aircraft and see that. We should have some kind of mechanism to simulate it. So the other one is when you want to develop the engine, what kind of safety computational modeling you should have to model the instead of component to the complete engines, and what kind of numerical techniques you have to use to get it. So if you talk about any new engines, we talk about the generation of the aircraft. Maybe as an aeronautical student, you can see that what kind of generation of aircraft, the first generation to the current generation, we talk about 5th generation. So what kind of, other than the parameter, stealth, what is the radar cross section? RCS means radar cross section. What kind of radar section you should have? What kind of infrastructure, that infrared signatures? This basically is a stealth point of view. So super cruise data, super maneuverability. What kind of smart system you should test so that your enemy cannot detect, and what kind of weapon, because we are talking about the military. So we are always carrying kind of weapon. How to, what kind of weapon, that weapon, how to hide it, how to not your enemy to detect. So that all that, because in the earlier generation, they never talks about this. The current 2020 onwards, people more than your, now we know how to, for a given engines, how to produce a gas turbine engine. Now, but some of these modern technologies are not incorporated. So as a student, these are the future keywords or technology people are working towards that to achieve this. This all you can call refinement or improvement over the current technologies. So this is the roadmap, like you maybe seen the GTRE of this. So GTRE, we talks about 80 kilonewton thrust plate somewhere here. So you talk about these other engines. So right now we are working towards these engines, and future generation will be around this. This is comparing around 100 plus. I don't know 80 to 100, and people are already working towards 200 plus kind of Newton thrust class engine. So this kind of technology, you can see that what we are proposing that right now we are around here. We are planning to move around here next our development. Then catch up later on with pressure ratio of 30 with in agreement with the other world. So if you put in terms of technologies, this is the way as a GTRE man to get, if you want 110 kilonewton thrust, what kind of technology we put all this, what each component wise, what are the technologies we have to put it. So I told, no, I am from the outer Banana. I have put it, this all the future technology we should have from that. So that's why you required, as far as your students wise, if you talk about, we have lot of work to do, lot of opportunity available. As a GTRE, you can come for, mostly the restriction from our side is, we cannot allow more students come and join. One or students can come and work for the training for during your BTech time, 1 or 2 months time, just to come to know what kind of work we are doing, what kind of technology we are using. That's for 1 or 2 months. But as a final year BTech project wise, mostly we won't encourage, because 2 to 3 months time we cannot do some effective smart work. So mostly we won't allow for students for the final year BTech, but as a trainee in between month, maybe your second year or third year, you can based on, you can request your HOD to write to our director GTRE or any of the DRDO labs concern based on your requirement, whether it's ours is engine, there is electronics lab, there is aero labs or aeronautical labs or that. So you can apply and get your training just to come to know what is happening all around us, so that you know that what kind of technology or where we are, as in India, where we are, what kind of technology we are. Are you far away from the other countries, or where we are, what are the difficulty we are, how to move forward that way. As far as the faculty is concerned, there are a lot of work, there are a lot of resource available from DRDO. One is cars, means that under 10 lakhs you can take any small work, you can approach any of the lab, you can able to demonstrate small technology, you can do it. Then other technologies that ARDP, this one, you can write your proposal to the Aeronautical Development Board based on your facility available or what kind of facility you want to develop. You can use that fund to develop your technology and motivate the students on that. The other one is that the recent one is called the COPT, Center of Propulsion Technologies, right now under the IIT Bombay as well as IIT Chennai this. So you can contact this to nodal agency if you want to have further any other modern technology you want to develop or you interested. So these are the resources available as far the faculty is concerned to tap from DRDO to do that one. Students is concerned, MTech students always, I'm not talking before COVID. During the COVID, we are not allowing anybody. But students wise, BTech students, trainee will allow, maybe 1 or 2 from college, not more on to that. Finally, BTech student, we discourage this, 1 or 2 can come, but we will discourage. But MTech, yes, similar way, maybe 3 or 4 students can come and do this work for carrying out your MTech thesis work. So that's all from me. Over to Professor Vijay Raja.
Okay, thanks,
Okay,
Dr.
sir.
Ganesan.
Yeah, thank
Really,
you.
it was a very nice presentation, and moreover, a lot of innovation we learned from this
Only thing
webinar.
mine is so abstract, because each one have the different technologies. So it's required
Yes,
more
yes,
time to do
naturally.
that. But my aim to only give the words, at least from the word you pick up, then you do further research, you can know what kind of technology you required all this.
Yes, thanks, Dr. Ganesan.
Yeah.
And moreover, he told something faculty benefit
Yeah,
as well as
faculty
the
also, yes,
students
like I
benefit.
told now, there is one option to cars, second to ARDP, the second one is the
Yeah,
propulsion.
surely we'll take it forward and do the things with your support and guidance.
Definitely
And
we
very
will do
soon
that.
we'll meet you in person if the DRDO or the GTRE permits, means because during the COVID times it's very difficult to approach the people.
Yeah,
But
yeah.
after the COVID, in the month of December or January, we will try to meet you in person. And in the meantime,
Okay.
we'll let you know that what are the opportunities available to get the
Okay. Our side will
parcel, so you
support,
can
no
utilize,
issues.
try
Yeah.
to utilize that one. And we'll prepare the proposal for ARDP. So already we
Okay.
got one project with ARDP with the support of
Okay, good.
DRDO,
Yeah.
Dr. Badu sir. It's already
Mm-hmm.
informed you. And thank you very much for accepting our invitation and given delivery a very good about the friends in guest application. So it was very useful for our students, and moreover, apart from the lectures, whatever you told about that facility available, training, as well as the opportunities in various lab, DRDO, DRT lab, so it may be very useful for our students. Really, I thank you. Now
Thank
I
you.
request our faculty, Mr. Venkatraman will deliver the vote of thanks.
Okay, thank you.
Okay, thank you very much, sir. I think you have done my job, majority. I would like to thank Dr. S. Ganesan, Group Director, GTRE, for joining with us. It's not easy of your rank to spend time for students. I thank you again, sir, for giving your
Thank
time.
you. Yeah.
I was loving the entire lecture. I was wondering that your lecture has got has addressed all part of the students. As you know, sir, we have second year aerospace and second year aeronautical, third year
Yeah.
aeronautical, and final year aeronautical who have joined. So your lecture has addressed all students of second, third, and fourth level. I would like to thank you for addressing all
Thank
students.
you. Yeah.
And at last, it's very appreciable that we had some as a faculty to take away. We have completed a cars project by DRDL
Okay.
in the year of 2016, and we love to write a proposal in the cars in your laboratory.
Definitely.
I think as HOD has rightly pointed, we'll discuss and we'll get you, sir.
Okay. Yeah.
Thank you. On
Thank
behalf
you.
of
Thank you.
management and Department of Aeronautical Engineering, I convey my thank you, big thank you, sir.
Thank you.
That's
Thank
from
you.
my side. I think there are no questions. If you have questions, I think you can post it. We'll get it answered through, sir. Thank you very much, sir. Again,
Yeah. Thank you. Thank you. Thank you. Thank you. Bye.
thank you.
Thank you, Dr. Ganesan.
Thank you.
I
Thank
will
you.
call you in the evening time. Okay.
Okay. Thank you. Thank you. Bye. Bye.
Thank
So
you,
good
sir.
evening, sir. I have some doubt. May I ask,
Okay,
sir?
Yeah.
bye. See you all.
Yes,
Go
please.
ahead.
So
Yeah.
good evening, sir.
Good evening.
Actually, when it comes to
Yes.
self-fighter jets, how we are trying to manage to reduce the heat signatures from the jet engine, sir? As already the Americans are familiar with that thing with F-22s and F-35s, how we Indians are trying to reduce the heat signatures?
Once again, you come. I am not able to get clearly. Tell once again.
Sir, actually, when it comes to self-fighter jets, we are
Ah,
very dependent on reducing the heat signatures from the fighter jets, right, sir?
correct. Correct. Yeah.
When it comes to American fighter jets, they are already familiar with the F-22s and F-35s.
Yeah.
From
Correct.
Indian point of view, how we are trying to reduce the heat signatures right now?
See, basically, the Indian side that like I talk about no emissions and other one. So our this one right now, like I said, now the end of my slide that the stealth and other point we are not addressed. Now we are trying to address it. One is through the infrared predictions. So how to reduce it? So right now, one of DRDO lab itself is working on the reducing your IR signature levels. So that way you can do. Then also we are working on the smart material and thermal coating over the blades and other your heat seats. So we are working on that, but none of this technology we are incorporated any of the engines. Right now, all in the R&D stage. So we are not put in there, no, but we are parallelly working into the different methodology to arrive what kind of a stealth mechanism so that you can able to predict your heat flux or hide your heat shield from the other engines.
Thank you, sir. Is GRTO is working with the AMC, the new model of the fighter aircraft that India is
Yeah,
developing, the fifth generation.
yeah.
Sir, how is it doing with that, sir? And what about the Kaveri engine? Why it is dropped out from deploying in the AMCA?
No, the requirement is changed that then meantime the requirement for the aircraft thrust level also increased. Right now the requirement 90 kilonewtons. So our like I said, now our engine is 80 kilonewton engines. From the aircraft side, now it is increased to 90 kilonewton engine. So we are planning to develop the new engines to meet that one. So meantime, we are having the other resources to use that aircraft.
Thank you very much, sir. Thank you.
Yeah. Okay.
Excuse me, sir. Sir,
Yeah.
sir, I actually had a proposal. Sir,
Your voice is breaking. I would request you to be a little bit clear.
sir, actually, I had as you said, you are in afterburner design, sir. So
Yes.
I actually had a proposal, come question, you can say, that
Okay.
since we are talking about fighter jets, the fighter jets move at plus 1.1, even without afterburners, or more than 600 and 900 kilometers per hour normally, sir, during cruising.
Yeah. Yeah.
Not
Okay.
wrong. So, sir, during that time, there's a tremendous amount of airflow over the engines and over the airframes, sir. So
Yeah.
we are using fuel to increase the temperature in the afterburner and then add the spark and ignite them, sir. I was
Yeah.
just thinking that if you could use some mechanism to generate, use EMF or electromagnetic flux by adding a simple mechanism like, because the airframe is metallic and the parts inside the engines are metallic, magnetical circuits around, it would generate EMF and we could use electric propulsion for the afterburner to help support afterburner. So, and that electric propulsion can give a lot of thrust if it's used properly. So, sir,
Yeah, to tell you that as far as the electric propulsion overall technology in the country talk about, so we have the plan, but not now, maybe after 5 to 6 years time the line to develop the electric propulsion and work on to that. Right now we are not working any of the electric propulsion technologies because the requirement, whatever we have the mature the technology, use this technology, develop the engine and give it to that, because this is required a separate R&D from electronics to the electrical system. So we have the plan for the develop the electric propulsion, but as of now we are not planning to put it any of this, but we have the plan to do use the electric propulsion into that. If you have any proposal or anything, that definitely will, you can send to me. I will go through that. I'll talk to my management. If something is useful, we can develop something on that. Welcome.
right, sir. Okay,
Okay.
sir. Thank you, sir.
Okay.
So, what do you think about the
Okay,
future of
thank
hybrid jet engines, sir?
Tell once again.
What do you think about the future of hybrid jet engines, sir? Is it possible to develop it in the upcoming
It's
future?
no possible to develop. If you talk about the future one, we talks about all the man to the unmanned. So right now the whole technology is to, you talk about man to unmanned. We don't want so sophisticated. Even GTRE, even and I am not covered my. We are working towards uh, towards a manned aircraft to the unmanned. There you record somehow whatever the technology you learned, use it, and because you are going to use unmanned propulsion, forget about all kind of this, but the technology can be used to get it. So what we are, as with GTRE, we are planning to the use whatever the technology you learned as much as possible, try to push it without investing so much on new technology used for R&D. Like I talk about the 5th generation aircraft, there we are trying to use the, when you want to go for a higher thrust class of engine for the manned one, like I talk about 110 to 150 kilometers, there we try to use all kind of technology and go ahead. As far as the current world moving towards the more than powerful, they talk about more smart technologies, smart material, all this. So we have moved towards that. In that way, GTR also we are moving towards that technologies.
Thank you, sir. Thank you.
Okay.
Okay. Thank you, sir. I think
Thank you.
students, if you have
Okay,
any other questions,
thank you,
you can
Dr.
write to
Thank
Ganesan.
us.
you. Thank you.
If any
Thank you.
question is,
Yes,
we
sir.
can post it. Please,
Okay. Yeah.
students.
Okay.
Thank
Thank
you,
you.
Dr. Ganesan.
Thank you. Thank you. Bye.